as needed lah. It means that not every week we will have tutorials. I will announce if we have tutorials. Okay? Yeah, because I plan to move the Friday class to Thursday afternoon, but some of you said they have classes at that time, so I have to cancel that idea. So, any more questions on the class schedule and also coursework? Yeah, if you have any questions, you can contact me. You can email or you can WhatsApp. Or since all of you are in campus, you can come to my room. Okay? Okay, now let's start. So today we are going to learn about finite difference. How to solve differential equations. And you see, most of the physical problems are described in terms of differential equations. For example, F is equal to MA is actually a differential equations. Oh, sorry. Yeah, I forgot to record. Um. Okay. Now, so F equal to MA is a differential equations. If and we can write it like this, right? F is equal to M dV over dt. This is differential. Okay. So how do we solve differential equations? Like you have studied in your previous class, right? In your first year mathematics. If we have, like, for example, this differential equation to fx, we have this condition, f0 is equal to 1, we can find the exact solution, right? This is quite a basic differential equation. So what is the exact solutions? So fx equal to exponential of x, right? But how about if we have something a little bit complicated, like this? This is heat, steady state heat conduction. Steady state. With heat generations. This is with heat. For these equations, it might be a little bit difficult for us to solve, to find its exact solutions. right? Okay. So, let me know if I am too fast, okay? So, how do we solve these types of equations? Okay. Basically, for differential equations, we can solve using analytics method. In analytic methods, you can find its exact solutions. However, sometimes it's quite difficult to do so, and sometimes that PDE do not have the exact solutions. And another way of solving the DE is using numerical method. Numerical methods, we have a few of numerical methods. One, which we are going to study in this class, finite difference. We also have finite element different method, finite element methods, and also finite volume methods. In the in this course, we are going to cover only finite difference. So when we say finite, it means that it finite points. Finite only refers to finite points. And in terms of algebraic approximate. Okay? Bear in mind that numerical methods can only find and approximate and approximation solutions, not the exact. So how? Okay. Do you still remember these equations that you have learned before? Maybe many years ago. Okay. For a small value of h, its derivative can be found using these equations. So this equation is what we call Taylor expansion series. So how do we formulate the Taylor expansion series? It's like this. Let's say we have a graph. This is x and this is x, right? And we have curve. A derivative is the slope of the curve, right? This is x, right? This is x plus h. This is x. This is f plus h. This. So the slope here right, f prime x we can define as f x plus h is f x. Alright. So this is basically how we derive the Taylor series. Get the idea. Taylor series. So now let's go back to our finite difference method. Okay. So in finite difference method, we are going to find numerical solutions. In the form of discrete function. To solve DE. Okay. Let's say we have an equations we usually call a governing equations. Right? The heat equations, elastic equations, material modeling equations are derived by governing equations. Let's say our governing equations is d squared y over dx squared minus dy over dx plus y is equal to 0. So our range is 0, x is from 0 to 10, and our boundaries at y0, at x0, y is equal to 1, at y10, at x10, y is equal to. So from these governing equations, from these DE equations, we will form matrix equations. A I is equal to B. And then from matrix equations, we will get our numerical solutions. Y equal to inverse of A matrix. Our solutions is a discrete function. This is x, this is y. This is the function yx. So the solutions that we will obtain from DE is actually a discrete thing. The DE formulations that we are going to learn is actually here. From differential equations into the matrix equations. Right? So far clear? Any questions so far? All right. That's good. Okay, now let's look for an example, a classic examples. We have these previous equations. And the condition is at x0, f is equal to 1. We know that the exact solutions. We know exact solutions is x. So find the finite difference approximations for x equal to 0 until x equal to 2. Okay. What is our first step? So the first step is to find the grid numbers. How many grid we want to have? Grid number. From x equal to 0. From x equal to 0 until equal to 2. How many discrete points we want to have? Let's say we choose n equal to 5. So we divide from x equal to 0 to x equal to 2 into 5 discrete points. Is 1, this is x1, this is x2, this is x3, this is x4, this is x5 of equal size. So our delta x 2 divided by 5, 0.4. If we were to tabulate the x value in a table, this is x, this is x 0, 0.4, 0.8, 1.2, 1.6, and 2.0. But we know that x0, fx is equal to 1. Okay. Then we will use finite difference approximations. X plus h fx is All right.
Excuse me, doctor.
Yes.
Doctor, just now you said that I got 5 points, but below the X got 6 points. So
What?
how does that work?
How?
I
Why
mean,
6?
just now you divided the two by five, right?
Yeah.
Then should be like 5 points, right? X1 till X5.
Two, 1, 2, 3, 4. Oh, why? Yeah.
Doctor, it should be 0.5.
Yeah, it should be 0.5. It should be this divided by 4. Right? This is 0.5, 1.0, and 1.5. Correct? Okay. Now let's get back to our finite difference approximate. So our one is equal to fx, right? Because our differential equations is so this. Let's solve for this. X plus h x divided by h x plus h x 2 h f is equal to f plus x plus h 2. Alright, we have is f x1 is equal to 0. So f x1 equal to 1. We have this, right? So we can find our f x2 is equal to f x1 1 plus h, right? And subsequently, we can also find our f x3 equal to f x2 1 plus h. F x4 is equal to f x3 1 plus h. F and f x5 is equal to f x4 is 1 plus h. Okay, so What is the value? So calculate this, and this is what we are doing. One, one, 125, 3.37, 62. Right? So this is the values that we will obtain from our finite difference approximations. Now, compare with exact solution. These exact solutions. So this is 1, 0.5, 1.6, 4, this is 7, 718, 1.4, 8, 2, 7.39. Okay, this is our edge solutions, and this is our finite difference approximations. So how do you think about finite difference? It's quite it deviate much from the exact solutions, right? Okay. Now, why? Because if the first reason is that because our grid is very coarse, right? We just divide it into 5 points. If we divide it into a finer grid, we will get a quite a good approximations. Right? I'll show you. Sharing. Alright. You see, this is something that I formulated using AdSense. So when we uh, divide our grid into 4, the results that we get is very very apa? It's not accurate. The accuracy is very low. Right? Only see this table. See this table. Just compare these two tables. Let's say we divided it into degrees. That's double degree. Maybe like 8. See, it's getting closer. The approximation is getting closer. Okay. Let's increase some more. Maybe 50. Hmm. You can see that the value of the finite differences approximations mm, do not deviate much. It still deviates. It's still not so good, but it's okay. Okay, maybe we increase a little bit more, 100. Yeah, it looks good. Any questions on this? By the way, stop sharing this. I'll share back this. By the way, these equations that we are using is we call it as this is forward, 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 or implicit. There's also another formulations that is backward. Or we call it as explicit. Now, for your exercise, um, use the explicit approximations to solve the previous questions. Alright? Let's take about 10 minutes. Alright? If you are done, you can write the answer in the chat box. Okay? I'll see you in 10 minutes. Okay, are you done? So we can see that if we are using finite difference with backward uh, formula, for now, for n is equal to 4, we can see that it gives like the worst case of solutions lah. It deviates too much from the exact solutions. But if we refine the grid more, find the grid, it will closely if we refine the grid in the approximations will be closer to the exact solutions. Okay, that this is something that we will discuss more on the next class. This is what we call convergence. All right, I think that's all for today's class. Any questions? We have no questions. Okay, I'll see you next class. Wednesday, right? Same time. On Wednesday lah. On Wednesday, I think Wednesday is 1st of June. 1st of June, 2022. So on Wednesday, we will talk more about convergence and also the forward, backward, and central differences. Okay, if we have if there are no questions, before you go, I just want to ask, is it okay if I conduct the class like this? It means that I don't actually use slides, or you all prefer slides? Yeah, because I thought it will be much slower lah if I write. All right, thank you. Okay, I'll see you next time. Thank you. Bye. See you. Sure, I'll share the PDF. I'll upload in the e-learn. Okay. Okay, thank you. Yeah, we will go in much detail about the explicit, implicit, forward, backward, and also central difference in the next class. Okay? Okay.